Okay, today we hear a talk by Till Baumann. Till is an observational oceanographer who studied in Kiel at the Geomar for his master's and did his PhD with Ilya Poyakov at the University of Fairbanks, Alaska. Then he did a short stint at the Finnish Meteorological Institute in Helsinki and has now been for the past 2 years with Ilka Fehr at the University of Bergen doing mixing in the Arctic. And today he will talk about the fine structure parameterizations of mixing.
Yeah.
Thank you for being here.
Thanks for the intro. Well, now it looks, of course, very different. My share screen. Do you see my shared screen?
Yes.
And the presentation in full mode? Great.
Yes.
Right. Yeah. Thanks for the intro. So the title is Quantifying Turbulence from Standard Observations. This revisiting fine-scale parameterization in the Arctic Ocean, and that's a story I've been developing together with Ilka Fehr, Kirsten Schulz from AVI, and Volker Mohrholz from Warnemünde, and it's currently under review at JGR. So why are we interested in turbulence? Well, turbulence mixing is a key process determining the Arctic Ocean state and future trajectories, but direct measurements are notoriously complicated and difficult to get to. You can see this on the picture on the right, that it takes 3 people plus 1 taking a picture to do one single microstructure cast. Whereas moored instruments, like for example at MOSAiC, there was this long ranger moored under the ice that was measuring for months and months without any supervision. So these standard observations are much more readily available, and and it would be great to use those to get estimates for turbulence. So this is the angle I'm using fine-scale parameterization with. I know there's lots of people doing like other aspects of it, trying to get the best estimates for models or like developing the theory, but my angle is just to test basically the observations of the observation side of it. Why is mixing so important in the Arctic? Well, we have this huge reservoir of heat that is the Atlantic water that is sitting underneath the cold water. And even very small heat fluxes of the order of 1 watt per square meter can have a significant influence on the sea ice. And on the right, we can see this nice sketch from Leonard Al from the book chapter, where you can see all kinds of Arctic mixing processes and an estimate of their amplitude. And we see that the internal wave breaking is labeled as 1 to 10 watts per square meter. So it's quite a significant amount. And as you all know, this is the only part of mixing basically that we have a hope to parameterize from standard observations. How we do this, I mean, you all are the experts, but just in case somebody is not so clear about this. So internal waves are ubiquitous in the ocean, and the energy contained in internal waves can cascade to smaller scales. And the idea is that this cascade is well known, so that the relationship between energy on large scales and the energy on very small scales to turbulence is well known. So fine-scale parameterization uses this principle to quantify turbulence on small scales based on observations on very large scales, 10 to hundreds of meters. And this is a very well-known method. I mean, it has been developed in the 70s and 80s and has been applied many, many, many times. But in the Arctic, there's still some complications, and the application is rather uncertain. And our goal was to evaluate the classical fine-scale parameterization in the Arctic over a large range of parameters, because there have been studies doing fine-scale parameterization in the Arctic, but they typically had very small data sets or no real way to verify what their results were. So this is what we use in terms of our data. We have collected data from 8 different Arctic cruises. As you can see in the map, they're all in the Eurasian sector of the Arctic Ocean, in the Barents Sea around Svalbard, but also in the Central Arctic from the MOSAiC expedition and the N-ICE 2015. And all of these cruises that we have collected have continuous ship ADCP measurements, or like for the case of MOSAiC and N-ICE, there was ADCPs mounted under the ice to get even better velocity profiles. We have some of them have ADCPs, and then we have all these profiles of hydrography. And the very important thing, or the thing that takes this data set apart, is that for every single data point that we have for our Finescale parameterization, we have direct measurements of epsilon from microstructure profilers. So every single data point you see on the map, we have both Finescale parameterization and epsilon over the same depth range. And you can see the profiles, cruise average profiles, I should say, on the right-hand side here for shear, stratification, and the direct observations of epsilon. And you can see that all of these quantities spread about 2 orders of magnitude. So we have quite a range of parameters, not just one very narrow band. You can also see by the thickness of the line, so where the line gets thick, this is the part of the profile we actually used for Finescale parameterization. So we couldn't often use the whole profile for reasons I'll go into shortly. But yeah, so you can see roughly the depth range we covered with our Finescale parameterization, and then yeah, we did our analysis. Right, about the Finescale parameterization. This is the bit you all know more about than me, but I'll give it a little intro anyways. So in a nutshell, as I said before, the internal wave field is quite constant for the world ocean. That is the assumption anyways. And it has been described by Bergen and Monk with their empirical model in the 70s. And this Bergen and Monk model has a known energy dissipation. And now the idea is that every observed internal wave field can be compared to Bergen and Monk, and accordingly the dissipation rate can be scaled accordingly. This is how the parameterization looks like. This is how the formula looks like. And from like my observation point of view, it's just like, how do I get numbers to all of these variables? And the first term is quite easy. Epsilon naught is just a constant. And then you have n squared and n naught, and you get this quite easily from profiles from hydrography. This is what we have in stock. The next term is the shear variance compared to the shear variance of Bergen and Monk. And for this, we need the internal wave properties. We need shear spectra. And we get those, of course, from the velocity profiles. So we have velocity profiles, make them to shear profiles, make them into vertical wave number spectra, and which we see on the right-hand side here. And then we integrate those to get the shear variance. And yeah, this is then compared to the shear variance from Bergen and Monk. And the next term is basically just the ratio between shear and strain, which is basically the ratio between the shear spectra and the strain spectra. And the last term is a simple latitude dependence. So with this all in hand, I thought, okay, how hard can it be? Turns out it's a bit more involved than that. And there's a few special complications in the Arctic. One big problem are the double diffusive staircases. This is just a time series of weekly temperature profiles from MOSAiC. And we see that we have persistent double diffusive staircases beneath the halocline, around 200 meters depth or so. And in these staircases, we can't expect to have an internal wave continuum with weekly nonlinear wave-wave interactions. So the Finescale parameterization just breaks down in these regions because other processes take place. So we have to avoid them. And this can be a bit problematic because In the central Arctic, that means, so we have to avoid the mixed layer, and we have to avoid anything with double diffusive staircases. So the usable range is quite reduced. And this also means that the bandwidth of our spectra can be quite reduced, sometimes leaving us only like 3 or 4 data points in the spectrum because we have a limited depth range to use. But this is not all the problems in the Arctic. There's also that the internal wave field itself differs from mid-latitudes in terms of amplitude, composition, and bandwidth. And the Galois model, of course, famously developed for mid-latitudes, might not fit that well. So if you look at the amplitude, it's very well known that tides cannot propagate in the Arctic Ocean. So we are north of the critical latitude of effectively all tidal constituents that matter, especially M2 and K1, of course. And the sea ice and solidification hampers the generation of near inertial waves. So we have a historically very weak internal wave field, which is usually well below GM levels. And this is just an example from one paper, Levine et al. 87, just to illustrate how like observed spectra in the Arctic, just the typical pictures that they are well below any GM spectrum, typically several orders of magnitude. And this can make it difficult to resolve internal wave properties. But for our data, it doesn't look that bad. So the classical GM is the black line here, J equals 3. And we see that most of our spectra are beneath this, but not ridiculously far, so less than an order of magnitude. Mostly because we are in a relatively active region of the Arctic. This would look probably different in the Canadian basin or so. But in our region of the Arctic, the amplitude does not seem to be a big issue. So we can still resolve our properties okay. Another known issue is the composition of the internal wave field. Because there's no tides basically, the internal wave field is mostly made up by near inertial waves. And this means that the R omega, the ratio between shear and strain, tends to be quite high. Like a pure inertial wave has a R omega about 50. And we see this in our measurements that R omega has a huge spread, an average of about 10. Yeah, and that indicates a dominance of near inertial waves in the internal wave field. One issue with this is that near inertial waves, as they are generated by storms or wind events generally, can change over time. So the prerequisite of a constant background internal wave field might not be true if like a storm comes through and pushes the internal wave field and makes a temporal change in the internal wave field. So this is something to keep in mind. Another aspect of the composition is the shape of the Galois model. If you look at the GM76 formulation of the shear spectrum of Galois, we have the parameter J star that determines the shape, and the canonical value is J equals 3, but it is long known in the Arctic that this does not always fit best. So this is an old figure from Basaro and Moorhead in 1991, incidentally the year I was born. And this shows that the horizontal kinetic energy spectrum, they did a fit to Galois and had J star as a free parameter. And you see that J star equals 3 is probably not a good idea. And they find in different parts of the spectrum, different values of J star that fit best. For this part of the spectrum, it was J star equals 60. And for the higher wave number range, it was J star equals 20. So there's a huge deviation of that. For our spectra, so this is again the shear spectra, and here I just, it's the same spectra, but I just converted them to horizontal kinetic energy by multiplying with 4 pi k squared to get them into kinetic energy spectra. And the gray lines are Galois-Monk with different values of J star. So the classical J equals 3 is the black line here. And then we have 5, 10, 20, 30, and so on. And the pale line here is J equals 100. And what we can see is that, yeah, J equals 3 might fit well to some of our spectra, but not to all. So there is quite a bit of difference, sometimes in the shape of the spectrum, where, yeah. So this is something to keep in mind. I looked into changing J star in Galois-Monk or do a fit to it, but then I rapidly decided that this is going too far and I can't deal with this. So I just kept it as is, but this is something to keep in mind. Now, about the bandwidth of internal waves. Well, internal waves exist on frequencies between N and F, as everybody knows, but in the Arctic, F is very high. And if we have the bandwidth expressed as N over F, then in the Arctic, we have a very much reduced bandwidth if we don't have vastly increased N as well. Yeah. This is supposed to be corrected by this latitude dependence term that we have in the end of the Finescale quantization. And in our results, this is just a sneak peek, we see that for all of our data points, the bandwidth of the internal waves is between 10 and 40, as opposed to about 71 or 72 it was, I think, for the Galois-Monk. So we have much reduced bandwidth, but we couldn't find any dependence on the epsilon result on bandwidth. So it looks like this correction term is working. And even though we have a much reduced bandwidth in the Arctic, we didn't see any major influence on the final result of the dissipation rate. Okay. Yeah. Right. With so many caveats and so many challenges listed, let's move on to the results that we actually got. Right. So again, this is like all the data points that we have from all of our cruises, and then we perform fine-scale parameterization using the ship ADCPs. So we get the shear spectrum from the ship ADCPs, the strain spectra from the CDD cast or MSS cast actually, do our fine-scale parameterization, and then compare it to direct observations of epsilon from the microstructure cast. We only get one value for each profile because we have a limited range. So we have between like, I don't know, 200 and 400 meters of profile. And this is only good enough for one value of fine-scale parameterization. And we also averaged with a geometric mean the direct observations. So we have one value of epsilon for observations versus one value of epsilon from fine-scale parameterization. And yeah, here you can see them plotted against each other. X-axis observations, y-axis fine-scale. The big dots are cruise averages, and the small dots are each individual data points. And the perfect fit would be on the black line in the middle. And as you can clearly see, it's not perfect. But the dashed line is a factor of 2. And that's not too bad. I mean, this would be still considered excellent in turbulent terms. And the dotted line is a factor of 5. And all of our fine-scale estimates are within a factor of 5 of the direct observation. So like at least in the cruise averages. So this is not too bad. We're quite happy with this. But there is quite a lot of variability in the individual data points. That's something to keep in mind. And what sticks out is really that the MOSAiC observations look quite bad. MOSAiC, we have split up into 3 drifts, one here, and one here. So it's the green, brown, and pink. And we see that they have like the huge spread here, with basically always the same observations and a huge spread of fine-scale parameterization. So we will look into this later in the discussion and figure out what's going on there. But yeah, for now we can move on and look at how the results look for the lowered ADCPs. So lowered ADCPs that are attached to CDD rosette have generally better resolution and lower noise level than ship ADCPs. And this can be quite nicely illustrated here, where we have spectra of ship ADCP and LADCP from the same cruise. These are shear spectra, and the yellow line is the noise shape. So whenever a spectrum is parallel to this yellow line, it's noise. And we see that for the ship ADCP spectrum, it sort of approaches noise level over quite a long range. It's difficult to see where it actually is noise. I set the limit to here, but could also set it here or here. So it's difficult to see where it actually approaches noise level. Whereas for the LADCP, it's very nice. It's very clear, very flat spectrum, and a sharp turn to noise level. So it's very easy to pinpoint where the spectrum gets bad, and it's usually also a lot higher wave numbers than the ship ADCP. So unfortunately, we only had LADCPs at 5 of the cruises. But the results look quite promising. So this is compare the same cruises for the ship ADCP. For the LADCP, they look a lot better. Excuse me. But yeah, we can't really conclude lots of things because we have quite a limited amount of data points. But it was a quite interesting result, I thought. Another aspect of Finescale parameterization is the strain-only parameterization, because current metadata is a lot more difficult to get hands on. And we have in the Arctic lots of these ITPs, the ice tethered profilers that are drifting around. They have a huge wealth of data, but they don't have current data. So the question is how well could these be used to use Finescale parameterization to get an estimate of epsilon in the Arctic? Well, yeah, this is the parameterization equation if we use it for strain only. So we kick out the shear variance and replace it with strain variance. And then, of course, we have to make up a constant value for our omega. Canonically, this is set to 3, but we've already seen that in the Arctic, our omega is hugely variable and averages to something more like 10. So we used our omega equals 10 as a constant value and just used only the strain and had a look what our results look like. And it was not too bad. So the averages are pretty much pretty similar to as it was before with the full Finescale parameterization using the ship ADCP. And yeah, now it looks relatively similar, but the spread is quite a bit larger. So individual data points seem to have a larger spread and the error bars are quite big. But overall, on average, the result is surprisingly good. Yeah. So now I only want to talk about how we got these quite dodgy results for MOSAiC and all of the parameterizations that we did. So why does Finescale parameterization seem to over and underestimate MOSAiC so vastly, basically? So we're looking at the pink, brown, and green dots. On the bottom here, we see the time series of observations in black and the Finescale parameterization in colors from the MOSAiC drifts. And one thing sticks out is that for the first drift, where Finescale parameterization seems to underestimate, the observations actually look a bit dodgy. And we had a closer look into this. There's basically no variability or very little variability. And it turns out that the microstructure sound they used, the MSS, was the whole time a noise level. It was just that they were in the middle in the Arctic, in the middle of winter, measuring it under the mixed layer. there was just not enough signal for the MSS to work properly. And this step here is where they changed probes. So this is not data, this is something wrong with the processing probably. So our conclusion from this is that in this environment, FS actually looks a bit more realistic than our so-called ground truth. So this is something to think about. A little note that we do have data points that actually show lower observed values of epsilon, but these were done with a different microstructure profiler. These were done with Rockland Scientific's VMPs, VMP 2000, and they tend to have a lot lower noise level than the MSS. Right, but this MSS in noise level does not explain why suddenly at the end, when we are again in summer in the central Arctic, why Finescale formulation seems to overestimate a lot. So what's going on here? And the most intuitive explanation I found is that when looking at the strain spectrum associated to the last drift of MOSAiC, we see it's a very steep spectrum, and it's the only one that's steep throughout the wave number range, even at low wave numbers. So this spectrum does not compare well to J star equals 3 at all. So it looks like much more it compares to J star equals 60 or something, which would be one of these lines. And over the wave number range that we see here, the energies of these GN with J star 3 and 60 are very different. So we compare to this energy of J star equals 3 or this from J star equals 60 would lead completely different results. So this would be a reason to overestimate the Finescale quantization. In this instance. So there again comes the question, should we or could we modulate Baumann to use other J stars? And yeah, I decided that this is probably not a question for observationalists, but a question for somebody developing the theory to make this consistent and make it work so that it actually is meaningful. Right. This leads me already to my summary. This is again the summary of all of our results. This time plotted as Finescale polarization as a ratio to observations. So perfect fit would be now on the 1 here, with the factors of 2 and 5 again, with squares showing the lowered ADCP, the LADCP where it was available. Circles show the full Finescale polarization using the ship ADCP, and diamonds show the strain-only parameterization, where we can see basically all the plots I showed before condensed in one. For example, we see often like the larger range of the Finescale parameterization with the strain-only compared to the other estimates. Right. And the summary is that Finescale parameterization is a powerful tool to quantify turbulence. And we validated over quite a large range of parameters in the Arctic Ocean. And we found it works. However, there are quite a few caveats. So while the cruise average epsilon is aptly represented, individual data points might be quite off. So our takeaway from this, purely from observational point of view, is that if you only have like 3 data points, Finescale parameterization is probably not a good idea. And we find that an indication that substantially non-wide shear spectra may indicate that the internal wave climate at the station is probably not suitable for classical Finescale parameterization as it is. But yeah, this is just basically our finding from our direct application. So we don't have any theoretical background for this. And one general problem with Finescale parameterization is, of course, that it only works away from exciting sources of mixing. So anywhere we have turbulent production from tides or like tides at topography or other vigorous things, Finescale parameterization doesn't work. So that's just something to keep in mind for the observational community. that this is it's a good tool for very quiescent environments. And that's all. Thank you very much.